Okay, in this lecture we're going to solve a system of equations. And the ones we're going to give you are as follows. Minus 7x1 plus 0x2 plus 3x3 equals 4, and 9x1 plus 1x2 plus 4x3 equals 6, and the final one is 6x2, so there's no x1 in this one, plus 5x3 equals 6. Okay, so we're going to first set it up. The equations can be written as a system of ax equals b. And we're going to let a be minus 7, 9, 0. Then we're going to have a 0, 1, 6, and a 3, 4, 5. That's my A matrix. My B matrix is vector 4, 6, 6. And then we're going to have an identity matrix is equal to 1, and of course we're going to have a vector of x's is equal to x1, x2, x3, and the objective is to find the solution for the x's. Right, so what we're going to do is we're going to write this as an augmented matrix. So we're going to begin with minus 7, 9, 0, 0, 1, 6, 3, 4, 5. We're going to augment that with the identity matrix. And with matrix B, so 4, 6, 6. And we're going to do elementary row operations to find the solution, and the solution will appear right in this column here. All right, so we're going to do these elementary row operations, and that's where the solution will end up. So the first thing we're going to do is we're going to divide this first row by 7. So divide row 1 by 7, by minus 7. All right, so that gives us 1, 0, minus 3 sevenths, minus 1 seventh, 0, 0, and minus 4 sevenths. All right, and the other ones are the same as before. And, whoops, that's a 6. And the other one is 0, 6, 5, 0, 0, 1, and also 6. All right, so this is the first step. Now the second and third steps are to get rid of these two. All right, we want to make those zeros. And how do we do that? The way we do that is through these elementary row operations, and you can see if you subtract 9 times, so the first step is subtract. So this is new row, row 2 is equal to subtract 9 times row 1, the new row 1, from row 2. And the new row 3 is we subtract 6 times new row 2 from row 3, the original row 3. All right, so let's see what that is going to look like. All right, let's first do the first subtraction. And let's see if we can keep it. So we'll keep that first one the way it is. 1, 0, minus 3/7, minus 1/7, 0, 0, and minus 4/7. Now, when we subtract, we're going to end up with 0, because we're subtracting 9 times the first one, so 9 minus 0 is 0, minus 9 minus 9 is 0, and then we've got, we're going to subtract 9 times row 1 from R2. So 1 minus 0 remains 1, and then it's 4. 4 times 7 is 28, and then 9 times that 3 up here is 27. 27, because we're subtracting, that minus becomes a plus, so we're adding 27 and 28. That gives us 55 divided by 7. All right, we do the same thing for the other elements. So we get 9/7, 1, 0, and 78/7. And if we do the same thing following the instruction here, and you can work that out on your own, we got 0, 0, because we're subtracting 6 times this new row. This is our new R3, our new R2, and we get minus 295/7, minus 54/7, minus 6, 1, and minus 426/7. So you can see we're getting a bit more complicated here in terms of this particular matrix. Now, the next step is to make this a 1. All right, we now want to make this a 1, and to do that, we have to subtract, or pardon me, add something about row 1, or we can subtract something from row 1 or row 2. But in order to do that, what we end up getting in the end is the following. So we're going to keep this matrix here. We're going to, in fact, just keep that the same way it was before. Minus 3/7, minus 1/7, 0, 0, and minus 4/7. Then we get 0, 1, 55/7, 9/7, 1, 0, 78/7, and the final one is, if we do this subtraction correct, or this addition, we get a 1 there, And then this becomes 54 over 295, 42 over 295, and minus 7 over 295, and 426 over 295. So you see we've already got one answer, and that answer is this one over here, because we've got one element here, and that's that 1. So this is the answer to the first, or to x3. So this is equal to x3. Now we've got to find x1 and x2. So how do we find x1? Well, x1, we just multiply, so we got to get rid of that 3/7. So we're going to use that 1 in the third row to get rid of the 3/7. And we do that by adding to the first row, add to first row, come on, 3/7 of row 3. All right, so we have, if we multiply that 1 where I've got that little arrow up right here, if we multiply that by 3/7 and add it to this number here, we get 0. So if we do that throughout, we get 1, 0, 0. Minus 133 over 2065, 126 over 2065, and minus 3 over 295, and we get 98 over 2065. And let's just keep this other one intact. To the next step, 9 over 7, 1, 0, 78 over 7, and the final one is the same as we had before. So 54 over 295, 42 over 295, minus 7 over 295, and 426 over 295. All right, now we need one more step to get rid of that one and make that a 0. So we're going to make that into a 0. So how do we do that? Well, we've got to take, we're going to subtract, so it's row 2 minus 55 over 7, row 3. Okay, that will do it. So what does that give us? Well, that gives us, in the end, 1, 0, 0, minus 133 over 2065, 126 over 2065, minus 3 over 295, and 98 over 2065. And then the second one becomes, the second row becomes 0, 1, 0, and we get minus 315 over 2065, minus 245 over 2065, and 55 over 295, and minus 420 over 2065. And the final row is simply the one that we have before, 0, 0, 1, 54 over 295, 42 over 295 minus 7 over 295 and 426 over 295. All right, and now let's do that again. Let's look at this augmented matrix, and we find that the solution, all right, this is the solution. This is the inverse of A. All right, that's A inverse, and this, of course, is the identity matrix. Okay, so our result is that x1 equals 98 over 2065. x2 is equal to minus 420 over 2065. And x3 is 426 over 295. And then this, of course, is our A minus 1. So if we multiply A minus 1 by the original A, we should get that identity matrix on the left. And that's the solution. Now, we can write the rank of a matrix all right, is if the rank of a matrix is 0, that means that you've got some kind of a problem and you can't get a solution. So let me just tell you how we find the rank. To determine rank, the rank of a matrix, use elementary row operations. And remember, when we talk about elementary row operations, we find that you can also do the same thing with columns. All right, so we can have column matrices as well. And the rank of a matrix we find by using elementary row operations until the matrix consists of only ones and zeros. The rank then, the rank is the number, which we denote like that, the number of non-zero rows. And the column and the row rank, so number of non-zero rows, is equal to the column rank. So if you have a matrix that's 10 by 10 and you find that the rank is 8, using the row rank, that means that 2 of the rows are only zeros in it. Well, you'll also find that 2 columns are only zeros, and the other columns will have ones, at least one in them. All right, so what we want to go, let's look back at this equation. We want to solve A, X. X is a vector, A is a matrix, B for X. All right, and we found that using that solution method of elementary row operations that we just went through. And we have some criteria here. There's no solution if the rank of A augmented by B, so now we don't have that what do you call it, the identity matrix stuck in between there, like we did when we looked up the when we looked up the elementary row operations to get us a solution, both the inverse of A and the solution to the x's. And again, this is an augmented matrix, but a little different than the one we used before. And we find these augmented matrix using in R, where R is the system of the software package R, we can, and the term is concatenate, or that means sticking together or combining a matrix and a vector or two matrices. We can join them together using the concatenate command in R. In R, the concatenate command is if you're binding rows or columns. So in other words, if you have a matrix A and you want to add columns to the bottom of it, you'll use the command R bind. All right, and let's say that A, B. All right, what that does is it'll take the column, the vector B, and combine it, put it underneath the matrix A. Will this work in this particular case? Not necessarily, because B, we had a column vector, so you'd have to turn B into a row vector, and it happens to be 3 by 1 if it's a row vector. So let's just put that little prime there to indicate that that's a transpose of the B vector. So now it's a row vector. Then it works. Or you can do the columns, which we did up there. All right, if you use that column thing, then you can go R column A, B, and that'll combine them the way we want side by side. All right, you've got to make sure that the length of a row is the same across A and B, or in the case of columns, when you're concatenating them, the length of the column has to be equal to the length of the columns in A and in B. All right, so that's concatenate. And no solution if the rank of A augmented by B is greater than the rank of A. 2 is exactly one solution. If rank of A equals the rank of A augmented by B, and as long as that is, so that's equal to the number of unknowns. All right. 3. We get infinite solutions if the rank of A is equal to the rank of A augmented by B, and if that's less than the number of unknowns, then you get an infinite number of solutions. So if the rank of A equals to the rank of A augmented by B is equal to the number of unknowns, you get exactly one solution, this one up here. And if this condition holds that it's less than the number of unknowns, then you get infinite number of solutions. All right, I'm going to end there, and we will look at determinants and another way of figuring out the inverse of a matrix using Cramer's rule in the next set of slides. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.